Ulises Orozco Rosas received the MS and PhD degrees in digital systems from the Instituto Politécnico Nacional in 2014 and 2017, respectively. He has also held a postdoctoral position. From 2017 to 2018, he was appointed at the Department of Computer Science, Universidad Rey Juan Carlos of Spain. He is currently an associate professor with the School of Engineering, Cetis Universidad, and a member of the National System of Researches. His research interests include machine learning, computational intelligence, parallel and heterogeneous computing, autonomous vehicles, and mobile robots. He has published over 60 papers in peer-reviewed journals, books, and conferences. Without further introduction, Ulises Orozco.
For the presentation. Good morning, everyone. Welcome to the presentation of GPU, Accelerated Particle Swarm Optimization and Artificial Potential Field Algorithm for Mobile Robot Path Planning. My name is Ulises Orozco, and this work was in collaboration with Dr. Kenia Picos and Dr. Oscar Montiel. Well, the motivation for this work, actually, robotics is one of the most important technologies. Science is, it is a fundamental part in the automation and manufacturing. Nowadays, we cannot conceive the idea, the manufacturing industry without this part. There is an increasing demand of autonomous mobile robots in various fields of application. These robots just jump out of the factories to be involved in our daily life. There are several applications such as material transport, guiding people at museum, assisting teachers at museum and at schools, monitoring power plants like nuclear plants, electrical plants, and also the self-driving cars industry has an incredible increase in applications and changing the form that we transport people in some places. So this is the motivation and the importance to design algorithms and develop computational models for intelligent systems. And the main objective of this work. We are going to start with the definition of the path planning problem. So the main goal is to drive the robot, the mobile robot, from a start point to a goal point. So we start with a configuration of the environment. We are using a bidimensional environment. Imagine that in this room we have a camera on the sail, on the top, viewing all the room. So this environment is populated with several obstacles, in this case, these red circles. So our mobile robot is a particle. Is denoted by Q, and every state of the mobile robot is denoted by its coordinates, X and Y, and the angle of the orientation. So we know the position of the robot and the position of the obstacles. So all the environment is known. The main objective is to find a set of configurations that will drive the robot from the start to the goal. So we want to get all the configurations, all the points to reach the goal. This is a zoom in view of the path. This green path is a set of configurations or points, see? Yes, to reach the goal. So our proposal to solve the path planning problem is presenting the GPU accelerated particle swarm optimization and artificial potential field algorithm. This is a hybrid proposal, a hybrid algorithm that combine the particle swarm optimization. In this flowchart, we represent the particle swarm optimization mainly with these three blocks. The blue one, this first one, and these yellow ones. And the artificial potential field that serves as a cost function and also as a main path planning method. The path planning method is the artificial potential field, and the optimizer is the particle swarm optimization. So the cost function will be parallelized in GPU, and in the implementation we use a graphics processing unit, a GPU, to accelerate the path planning. So the main goal in this work is to find the best path in terms of path length, the shortest path length to reach the goal, and to reach the goal with a short time, in a very short time. That's the main reason we are using the GPU, to accelerate the process of the computation. So our proposal use as an input a data structure that is the map. The map contains the initial point, the goal position, and all the configuration of the environment, the position and the size of every obstacle in the environment. That is the information that require our algorithm. Then we initiate with a swarm of particles, an initial random swarm of particles. These particles represent the solution for the path planning. We codify in each particle, we have n particles, which codify the attraction in the repulsion proportional gains that will be used by the artificial potential field to generate the path for every path planning problem. This initial swarm of particles or initial proposal of solutions for the path planning problems is evaluated using the artificial potential field. First, we evaluate the potential field. Every particle represents a solution. The particle 0 represents the first solution, the first proposed solution, particle 1, the second one, and so on and so forth. So we create a total artificial potential field using the attractive potential field function and the repulsive potential field force. So with the first particle, we create a total potential field function for every particle. This surface represents the solution for the first particle, and we have a surface for every particle. So that's the main reason to parallelize the cost function, because in a parallel form, at the same time, we evaluate all the particles using the artificial potential field. The artificial potential field consists of these two main functions, the attraction and the repulsion. The attraction all the time is attracting the robot to the goal. And the repulsion, when the robot is near to an obstacle, the obstacle push away the mobile robot. This artificial potential field can be explained with a simple analogy. Imagine a piece of paper where the goal, imagine that this of paper represents this room, and the door is the goal for the robot mobile. So we pull down the piece of paper in the goal to create a valley. And every obstacle, the chairs, the tables, represent the obstacles we pull up, creating these hills or mountains. So if the mobile robot is a drop of water, for gravity, we'll find the goal. It's a simple analogy to explain these equations that represent the artificial potential field. So we calculate the total potential field, and with this information, we obtain, by the negative gradient, the total potential force. The total potential force will drive the mobile robot to the goal. As we can imagine in our analogy, this total potential force will drive the mobile robot step by step to reach the valley. So this total potential force create the path to reach the goal. Then we evaluate every possible solution. We evaluate the path length, the path that we create with the total potential function. We evaluate configuration by configuration. We obtain the path length on every particle, every possible solution. So this information, see, with this information, we obtain the best solution at this time. Then we update the information of the particles, the velocity and the position of every particle, because every particle represents a solution for the path planning problem. We update the information with this equation. First, we update the velocity. Here we have three important parameters. The inertia, and gamma 1 and gamma 2 are the learning factors, the cognitive and the social. This term represents the local information, the current information in this first iteration. And the second term represents the global information, the information for all the iterations until the current one. With this information of the velocity, well, we lost the pointer. With this information, we update the position of the mobile robot. Yeah, we have a second one. Thank you. Thank you. Sorry, we are live. Okay, with this information of the velocity, we update the position of every particle with the updated velocity and the current position. We update the position of every particle. Here we have a simple example of how this process of this iterative process is working. At the beginning, we have a random set of particles. The position is random, and the velocity also is random. Here in this example, every particle is represented by this blue circle. The vector of velocity are represented by these orange arrows. And the average position of all the particles is represented by the red cross here. And the target in this example, the contours of the objective function is here, located here. So at the beginning, all the particles are in every part of the environment. After several iterations, the particles starts to update the information of the velocity and the position. And this average position starts to move and it starts to reaching the goal. All the particles trying to be here near to the target goal. So after several iterations, 17 in this case, so we have a concentration of the particles near to the target. After 21 iterations, almost all the particles are concentrated in the target. And in 25 iterations, all the particles are concentrated at the target. The target for us is to find the best set of configurations that will form this total potential field surface that will drive the mobile robot to the target. So the output here, the output is the set of configurations, the path that will drive the mobile robot from the start to the goal. This is an iterative process. Our stop condition is the iterations, the number of iterations. So if the max of iteration is achieved, we stop the algorithm. If not, we continue with this process. We evaluate the new position of the particles, we update the velocity and the position, and so on and so forth, until we reach the max of iterations. Then we ask if we achieve the goal. If yes, we return the path. Every element of this array represents a configuration in X, Y, and angle orientation of the position of the mobile robot that will drive the mobile robot to the goal. If not, we display an error message. We test our proposal with several configurations. Here, with the limitation of the time, we have two different environments. A very simple environment for path planning, but at the same time, challenging for path planning algorithms. This one represents a trap for the path planning methods. Most of the path planning methods trying, based on the gradient, the negative gradient, trying to find the goal, following this path, and in some cases they are trapped in this part. Also, here we have a zigzag that represents a certain challenge for the path planning methods. The configuration for the results, we use a sum size of 16, but here we double to 32 because we consider the spin of the artificial potential field counterclockwise or clockwise. So because a swarm size of 16 by 2, 32, 64, and so on, until 1,000, 1,024 particles. The parameters, the best parameters for our proposal was the inertia, 0.7. This parameter was fixed in our implementation, but can be adapted dynamically. The learning factors were fixed at 1.5, and the maximum number of iterations, 10. The software CUDA 12.1, because we are employing parallel computing, Linux operating system, and C++ compiler 11.4. The hardware, Intel Core i9, and GeForce RTX 2080 for the parallel implementation. These are the results. In terms of path planning, we are looking for the shortest path. So the best results for the first map or environment configuration. So we improved the results the results are in meters, so the improve is very low in centimeters, but we can see in the standard deviation that the algorithm is very stable when the swarm size is bigger. The same with different environments. So we have an improved in every size of swarm evaluated. But the best results and the main target for this implementation was to accelerate the computation. The best result obtained in a parallel implementation on CPU was 8 times faster than the sequential implementation in CPU. But in parallel, in GPU, using the threads of the GPU, we achieved 133 times faster than the CPU implementation. That means that our robot will interact with the environment without a significant delay. This implementation, this is a first step where all the environment is known. But as a future work, we extend this implementation with partially known or unknown environments. With these results, we are capable of that because the robot will respond faster with change on the environment. As a conclusions, well, in this work, we present the particle swarm optimization and artificial potential field for mobile robot path planning, a GPU implementation. Our proposal demonstrate that can provide an effective and smooth path. Smooth path because we are using the artificial potential field. Effective because we reach in every experiment, all the time we reach the target if there is a solution for the path planning. Efficient and safe. Safe because we reach the target without a collision with the obstacles. The performance results show that parallel implementation on GPU accelerate the process by a factor over 133 times faster. That is the best result that we achieve. The experiment results indicate that this proposal can be extended for more complex and challenging path planning problems like dynamic environments and unknown environments where the mobile robot has to interact with its environment. Other robots, people, certain obstacles that change its position. So we can challenge more complex and challenging problems. Thank you so much for your attention.